I want to introduce the concept of voltage, which is also called potential difference. And I want to look at it. Voltage is really just the potential energy per unit charge, okay? And to get a sense of what I mean by that, what that means, I wanted to look at this thing here. Okay, so we got this is kind of fun, and we got these balls that'll roll down if I don't lose them all over the place. These balls will roll down. And you can think of this as charge moving through a circuit, okay? And what makes them move through that circuit? Well, gravitational potential energy does, okay? So if this is a circuit, gravitational potential energy makes it move through the circuit. And we can think of potential energy per unit mass. Remember, mg delta H is the change in potential energies. That's going to be the difference from the top to the bottom, mg delta H. Well, G delta H is an indication of how much potential energy per unit mass there is difference between here and here. So if I know G is about 10, and I know this delta H, how far this thing's going to go down, I have a sense of how much gravitational potential energy for a given unit mass an object will undergo as it goes through there. And theoretically, if there was no friction or anything like that, then we could say we know what the kinetic energy is. Well, voltage is like that. Voltage, or what we call potential difference, is really the electrical potential energy per unit charge, the difference from one point of a circuit to another point of a circuit. Okay, so I'm going to use the term potential difference interchangeably with voltage. I like potential difference better because it helps us show that there's a potential difference in potential energy per unit charge between 2 points on a circuit. Similarly, you could measure that difference in gravitational potential energy per unit mass for different points. What would we need to know? G and the change in height, the difference in height. So that's what really voltage is kind of like. I like the analogy here. Now I want to talk a little bit about a thing called Kirchoff's voltage law, and I'll definitely put this in more specific circuit terms in a minute. But think of this. Let's say the change in gravitational potential energy per unit charge between the top and the bottom is, let's just say 5 joules per kilogram. Okay, 5 joules per kilogram. I'm just going to say 5. Let's not worry about the units right now. If this is 5 more than this, well, then we can start to talk about what's going on here and here and here and here. Well, if this total difference is 5 and this is 1, then, okay, well then this and this, these differences have to all add together to make that total. So I can't have this is 1 and this is 4 between here and here, and between here and here is 6, and I can't have that. It has to add up to the same total. Let's make it easier. Let's make this 10. If this is 2, this difference is 2 from the ground to here, and this difference is 1. Hey, this has got to be 3, right? And if I come up here, let's just say that's a difference of 2. That's up to 5. Let's say that's up to 8. Well, then this difference has to be 2. It has to add up no matter how I go, whether I lift it up like this or whether I go from here to here and here to here and here to here, here to here, here to here. I have to undergo the same increase in potential energy per unit mass. Similarly, in a circuit, no matter how I get from point A to point B in a circuit, I will have to undergo the same change in potential energy per unit charge. Okay? So another way of looking at that is any round trip, the total change in potential energy is 0. I don't even need this for that. I'm going to lift this up. I lift it up here, and then I lift up here, and then here, and here, and here. Guess what? That potential energy total change was 0. Whatever I gained going up, I lost going down. Similarly, if I start here, lift up to there, go down to here, boop, 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 boop. Oh, when I get back to that starting point, the change in potential energy is 0. And that's the fundamental thing behind what's called Kirchoff's voltage law, is if I go in a certain direction around any loop in a circuit, the total change in energy has to be zero because you're back to where you started. You're back to the same reference point, okay? So let's take a look at that.
I'm going to talk about Kirchoff's voltage law. Kirchoff's voltage law is basically equivalent to saying that there's conservation of energy. It's an energy rule. And it means the change in energy from point A to point B, point A to point A has to be zero. And in this situation, and we're ignoring some things that could happen in changing circuits. But here we go. Let's think of a book. I lift a book and I do 6 joules of energy, put 6 joules of energy into it. I do 6 joules of work. I increase the potential energy by 6 joules. Then I lower it and I lose 2 joules. And I lower it again and lose 2 joules. You know, I'm not going to get into the whole lose or transfer. But 6 minus 2 is 4, minus 3 is 1. So it's got 1 joule of potential energy. I add a joule, I subtract 2 joules, I'm back to zero. Anytime I start at one position and end up back at the same position, the change in potential energy is going to be zero. Well, voltage works very, very, very similarly. Okay? Voltage is the change, I'll even write it this way, delta V, change in voltage from one position to another, the difference in voltage, and we call that potential difference, is the difference in energy, potential energy, per unit charge. So I'm going to say potential difference. I'm going to actually use potential energy, or change in energy a lot. But I really mean change in energy per unit charge when I'm talking about voltage. So if lifting a book here, boop, 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 back to the same spot, zero change in total energy, right? Change in energy is zero. Same thing happens in a circuit. Doesn't really matter how ugly the circuit is for our purposes. For a standard DC circuit, I've got a whole bunch of resistors. If I start at one spot on that circuit, and I say what happens is I go around the circuit. So start one reference point. That's going to be my reference point. You can pick anywhere, by the way, and you can pick any direction. But if I travel around this circuit and I measure all the differences in potential energy, difference of voltage between these 2 points, and wires have no difference in potential energy. There's no potential energy loss across wires, ideal wires. And I measure this one, and I measure this one, the difference between these 2 points, and so forth. I've got to come up with a total change of zero. So let's just say that's a battery. And let's say the battery has a voltage difference of 10 volts. And it really matters what's positive and what's negative. That's positive, that's negative, the way we draw batteries. Okay? So as I go in this direction, I gained 10 joules per coulomb, or 10 volts of energy, basically. Okay? Then if I go in this direction, this direction, this direction, I must lose 10. And in fact, if the current's moving like this, resistors, actually there will be what we call a voltage drop. So let's just say, in this case, this one is 5 volts, and this one is 2 volts of potential energy difference, and 3 volts of potential energy difference. Well, I go plus 10. In this direction, I drop 5. So 10 minus 5 is 5. Minus 2 in the direction I'm going, minus 3 is 0. So if I go in a round trip, around any loop, and there could have been other things going on here. I could have had something up here, and I could have had, I don't even know what this is. Maybe I've got like a television running over here, and I've got something over here, another resistor and whatever. As long as I go around a loop to come back to the end, doesn't matter what loop I go, if I figure out all the voltage drops, they have to add up to 0. Okay? So the way we use this is to figure out, if I didn't know this voltage drop here, I could say, okay, I went up 10, and then going around this loop, minus 5 is 5, minus 2 is 3. To get back to 0, I have to subtract 3. Oh, now I know that one has to be 3 volts. And this has to be the positive side, and that has to be the negative side. In other words, I have to go minus 3. I have to go 3 lower when I get there. Okay, so it helps you find unknown voltages. That's what KVL does. Kirchhoff's voltage law helps you do that. Kirchhoff's current law is useful for helping to find currents. And between this, KCL, and Ohm's law, we can do a whole lot, maybe not with a television in there, but we can do a whole lot of circuit analysis and make things a little simpler so we can find all the currents and the voltages.
Okay, what we have here is a battery in series with 3 resistors. And the battery is a 9-volt battery. Now I'm going to take the voltage probe and I put the black, which is the reference probe, there. And this says that the red probe is 9 volts higher than the black probe. So the delta V, the difference in voltage across, is 9 volts, with that red being the higher side, the higher potential difference. So that gives us the voltage across there. Now what I'm going to do is I'm going to start where that black probe is, and I'm going to start going around the circuit. And I'm going to figure out what the voltage difference is across each of the elements. Now the metal parts have no voltage difference. Okay, so now let's see that next resistor. And again, I'm going to go in order. So I did the battery. Now this says minus 3 volts. Minus means that that red probe is 3 volts lower potential energy per unit charge than the black probe. So the energy difference is negative 3. So if I start in that lower corner, I went up 9, and then I went down 3. So theoretically, that difference between the lower corner and where the red probe is now would be 9 minus 3 is 6 volts. In other words, the red probe there is 6 volts higher than the lower corner. And if we check that, yeah, we see that that red probe spot there, that part of the circuit, the difference between the lower corner there and really anywhere on the bottom of that circuit. Oh, and by the way, check. When I just had those both on the same piece of metal, there was no voltage difference. Now, continuing clockwise around that circuit, I've now found that there's a drop of 3 volts, that red probe is 3 volts lower. So from the beginning, 9 minus 3 was 3. Now let's get that last resistor. That's another minus 3. Well, that makes sense because from the lower corner, we went up 9, then down 3, then down 3, then down 3, and that gets us back to 0. And that means the potential difference, as you see here, between the bottom and the bottom has to be 0. Okay, think of, I climb up a big stair, and then I go down a little slide and another slide and another slide, and I arrive at the bottom. The difference in my potential energy would be 0.